Alright, so today we're going to be looking at sets. So just a heads up, we're going to be thinking about sets as groups of things. We're going to be thinking about them as listing all of the things that's within the set. And then we're also going to be thinking about them a little bit more abstractly and then representing the set as pictorially. Alright, so let's get started with an example. So if we say that we have capital A is the set. I'm just going to list out some numbers: 2, 4, 6, 8, 10. So the set is simply just the numbers 2, 4, 6, 8, and 10. And then if I say another set, which is represented by lowercase a, is simply just the numbers 2, 4. So we have two different sets, capital A, lowercase a, where capital A set is 2, 4, 6, 8, 10, and lowercase set A is just 2, 4. Notice that 2, 4, that comprises all of set lowercase 2, is also in capital A, 2, 4. So we know that set A is in capital letter A set, and that's what this symbol knows. This little C with an extra line in it is representing the set that's going to be in another set. So set A is in capital A. Alright, and let's take a look at original set capital A. There are 1, 2, 3, 4, 5. There are 5 elements. Of A. How many components, how many things are in set capital A? There are 5 things. How many elements are in set lowercase a? Well, there are just 2 elements of A. Alright, so that comprises like an example of listing out sets. Alright, so let's talk about some terminology. We are going to say lowercase a is a subset of capital A. So this is like this U shape, kind of like turned on its side, is how we mathematically represent set lowercase a as a subset of capital A. And we say that as A is a subset of capital A. But note, we are not saying A is equal to A. It's kind of an important distinction. Alright, we're also going to say set A is equal to set B if we have A and B. Have the exact elements. So for example, if A equal to set 1, 2, 3, and set B equal to set 3, 2, 1, that we could say that set A is equal to set B because they have the exact same elements. It doesn't matter if the ordering is a little funny or is it stated differently. As long as that there's a one-to-one that each element of A is also in B. Alright, we can say that set is not a subset of B. So A is not a subset of B. And then we can also say A is not equal to B if A does not have the exact elements of B. Alright, so that has to do with subsets. we're also going to be talking about some other terms that we're going to be interested in. So we're going to be interested in the union between two sets. So A union B. So once again, we got this, like this capital U shape in between. A union B. So if we were to talk about this in like a listing method, if we have A as the set 1, 2, 3, and we have the set B as in 3, 4, 5, then we know the set A union B is the set 1, 2, 3, 4, 5. So notice that the element 3 is in both sets, and we don't have to repeat it when we talk about the set A union B. We just state the element 3. So there's no need to repeat it. Alright, pictorial, if you want to think about this a little bit more abstractly, if we have what we call our universal set, all things that could possibly be in set A or B, we can have all of set A, we can have all of set B, and A union B is all of the space, all of B, and all of A would be this set A union B. It might be a better idea just to kind of use the highlighter. So here's all of A, and here's all of B. So A union B is all of A and all of B. Okay. We can also talk about the intersection between two sets. So A intersect B. Once again, we got that kind of big old U shape, but this time turned upside down. So A intersect B. So once again, if we have the sets 1, 2, 3, and the set B as in 3, 4, 5, A intersect B, well, that is just the element 3. 3 is the only element that's in both of these sets. Alright, if we want to think about it a little bit more abstractly and pictorial, we have the entire universal set, all things that could possibly be in A and also in or B. We could have set A, we could have set B. Well, the intersection of set A and B is just this middle region where both A and B overlap. So that is the intersection of A and B. Alright. We are also going to have the complement. So we're not talking about saying nice things to each other. We're talking about one set complementing another. So A complement, so A prime. This little symbol right here is indicating the complement. So A complement are all the elements in the universal set such that those elements are not in A. So that is how we mathematically express a complement. So let's think about this as a listing method first. So if we have the universal set, let's just talk about it being all the integers. So -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, and so on. All of those all the possible like numbers, both positive and negative. So let's assume that is a universal set. So let's assume that set A is all the odd numbers. So if the universal set are all the integers and A is all of the odd numbers, then we know that the complement of A is all the even numbers. So that's one way that we can think about complements, or kind of like listing them out. We can also think about complements a little bit more abstractly. We have the entire universal set, we have set A, and we have set B. Well, the complement of A is all of the things in the universal set that are not part of A. So we can do a lot of shading to represent the universal set, the complement of A, I mean. So the complement of A is all the shaded in blue area. So it's all things not A. Alright. We can also talk about the number of elements in A in a set. So the number of elements in a set, the number. So if A was the set 1, 2, 3, then we know that the number of elements in A is equal to 3, because how many things do we have in A? Well, we have 1 thing, 2 things, 3 things. So the number of elements in A is just 3. Alright, so let's do an example where we represent a set pictorially, and we're going to be interested in the number of elements in all sorts of different groups. So let's say we have the universal set. We have set A. We have set B. And we have 5 elements here. So when I say 5 elements there, I'm saying there's 5 elements in this little crescent moon shape area. So all parts of A that's not the intersection. And then let's say we have 10 elements, in that intersection region. And we have 15 elements in the part of B such that it's not part of the intersection. So that's what I mean when I say 15 elements in that area. And then let's assume that we have 25 elements that's not part of A or B, that's part of the universal set. So this 25 is all the elements that's in the universal set that is not part of A or B. So let's talk about the number of elements in some interesting areas. So the number of elements in A, well, that is simply this plus this. 5 plus 10 equals 15. The number of elements as part of B, well, that's just 10 plus 15. Alright, the number of elements that's in A union B. Well, remember, A union B, let's see if we can, is all the things in A and B plus its intersection. So that's going to be 5 plus 10 plus 15 is going to represent the number of elements that's in A union B. So 5 plus 10 plus 15, so that equals to 30. Alright, so what if we are interested in the number of elements that's in A intersect B? Well, if we remember, A intersect B is just that middle area, the area where A and B overlap. So going back here, there are 10 elements that's in that overlapping region. So it's just 10. Alright, let's say the number of elements that's in the universal set. Well, that's all of our possible areas. So 5 plus 10 plus 15 plus 25. It should equal to 55. Alright, so the number of elements that's in A complement. So one way that we can think about that, well, that is all the things that are not in A. So we can sum it up, all the things that are not in A. Well, we got 15 here and we got 25 here. Plus 25, which equals 40. Or, if you remember, A complement is all things in a universal set that are not part of A. And if we know the number of elements in the universal set, and we know the number of elements that are in A, then we know the number of elements that's not in A by subtracting the number of elements in the universal set minus the number of elements that's in A. So, the number of elements that's in A complement is simply the number of elements that's in the universal set minus the number of elements that's in A. So that will equal to, we know the number of elements that's in the universal set is 55, minus, if we already figured out the number of elements that's in A, minus 15, and that will tell us the same answer, 40. So it's just another way that we could kind of calculate the number of elements of a particular set. So we could also be interested in the number of elements that's in the complement of A intersect B. Well, one way that we can think about this is just sum up all the numbers that's not part of the intersection. So 5 plus 15 plus 25. Which equals to 45. Or, once again, well, this should be complement. We're trying to calculate the number of elements that's not in the intersection of A, B. Another way that we can think about this as being the number of elements that's in the universal set minus the number of elements that's in the intersection of A, B. So if we know the number of elements that's in the universal set, once again, 55. And if we know the number of elements that's in the intersection, so for us that's just 10, the number of elements in A intersect B. So the number of elements that's in the complement of A intersect B is 45 elements. Alright, so that does it for today's lesson.